So, last time we started to talk about seismic design and analysis. Should be analysis and design. You guys remember last time we started talking, if we have a building, a multi-story building like this, we said that it's impossible, not impossible, it's not computationally efficient to do multi-degree of freedom on a 3D building. So we need to simplify this building. I showed you how we can sum the stiffnesses if they are in parallel and series, and this by looking how this building is performing. So under earthquake, if an earthquake hit the base, this building is gonna make deflection something like this. All the masses of each story are gonna have the same delta, so all the columns in the one story can be summed as barrel series stiffness, okay? So we were able to convert a 3D building, that's not 2D, that's the 3D of the building. We can lump the masses and the stiffnesses of the building to be a multi-degree of freedom system. This multi-degree freedom system is gonna sum the mass of each story, and the stiffness of each story is gonna be something like this. Each one of these is the mass of each story. And let's say this is M1, M2, up to Mn. Same thing as the stiffness, K1, K2, and K3 up to Kn. How we can do this? You find the stiffness of this column, this column, this column. Let's say this is 10, 10, 10, so it's 4 by 10 or 10 by 10, depends on the number of columns. Sum all of them and get the equivalent stiffness. So this system is an equivalent system, to this building. And what is supposed to mean by this is the equivalent system? Like if you subject an earthquake or a lateral load to this building and this system, both of them are gonna give you the same delta. This one and this one, they are gonna give you the same delta. We said also that this system is still complicated. It's not a simplified system. That's a multi-degree freedom system. I don't know, like 1, 2, 3, 10 masses. So when we try to solve this system, it's still difficult. So if we want to make it much more easier, we need to do another simplification. This simplification is gonna be based on series stiffnesses, like this column or this column, K1 and K2 and K3 up to Kn are stiffnesses in series. So we need to sum them. And if you remember, the sum of these K, if they are in series, it's the absolute sum of Ki's. But if they are in barrel, sorry, that's barrel, and that's series, this is gonna be 1 over K1, this is K equivalent, and this is K equivalent plus 1 over K2 until 1 over Kn, okay? So these are in series, so if we apply the series summation of the stiffnesses and masses, we will end up with one big mass for the entire structure, M equivalent, and one stiffness is called K equivalent. And if we apply the same earthquake to this building and this building and this building, all of them are gonna give us the same delta. Like this building is gonna be something like this, and this is gonna be delta. And same thing here, this is gonna be same delta. If it gives you a different delta, so the way that we did it is wrong, okay? So all these systems are the same, but this is a first degree of simplification, and this is a second degree of simplification, and we call this system single degree of freedom system. Does anybody have any question for that? Okay, we said that It's just the stiffnesses and masses. However, in real life, that's not only the main thing, that the things that we need to sum. There's something called damping. We need to account for how the system is damping the seismic force. So when a seismic load or an earthquake hit a building, the masses and stiffnesses are resisting the earthquake, but also there's something is called damping. It's like a force, not a force, it's like a nature of the building itself or the frame system itself. Like when an earthquake hit a building, is the building is gonna be shaking forever? It's gonna stop at some point. What is stopping this from shaking? First is the masses, like the masses, the moment of inertia of the masses itself, and the stiffnesses of the column, and also the capability of the system to dissipate forces, and we call this damping. Like what? Like when you have a joint is opening and closing, and cracks open. When the cracks open, you dissipate energy. Heat, if you have a steel connection and the connection is keep open and closing, all this is as a capability of the system to dissipate the seismic energy. Okay, so we represent this by another element. Like every column here in this building has a damping force, and every story in every column has a damping force. So when we sum actually this, we represent the total damping of the building by something like this. It's like, do you guys know the piston of the car, like the hydraulic thing? We make something like this, and the stiffness, we make it like something, like when we represent the system mathematically, it is something like this, and this is K. So this is how the system is. When you study dynamics, you will understand what I'm talking about, but that's, I didn't want to put the damping, but I want you to let you know that we have systems that we consider them as a damped systems. So sometimes when we analyze a structure, we say multi-degree of freedom, damped or undamped. Do you consider damping or you don't consider damping? So if we don't consider damping, we are going to remove this. But if we consider the capability of the structure to have damping, we are going to consider C, which is the coefficient of damping. And also there's a single degree of freedom damping and undamped. Okay, so when you study dynamics, that's the first thing you do. Like you do single degree of freedom system, undamped. That's the easiest problem. If it's damped, that's more difficult. And then if it's multi-degree freedom undamped, it's like a degree of difficulty. If it's damped, it's gonna be much more difficult when you consider the damping. So that's also one information that you can keep it on the side. So, all right, so why we are doing this simplification? Because we are gonna introduce the concept of response spectrum analysis. Okay, we are doing this to get to this. What is the response spectrum analysis? So in earthquake engineering, we need to come up with something. We need to identify what is the base shear on the building. Like if this building got exposed to a specific earthquake, like let's say this is time, this is AG, the acceleration of earthquake, and the acceleration of earthquake is something like this. By the way, this is the acceleration of the ground, and this is a characteristic of the earthquake itself. It doesn't have anything to do with the building. Let's say LA, Los Angeles, got hit with an earthquake. So the earthquake has AG with this time history, okay? It has nothing to do with the building. It's gonna hit all the buildings in LA. So all the buildings are gonna have this, but the forces on each building is gonna be different. Depends on the soil, depends on the building itself, the framing system, the masses, the height, everything with the building. So we have an acceleration for an earthquake, and we need to come up with the force on each building, okay? So from my perspective, the force on each building, we all know that the force is MA, mass multiplied by acceleration. If we know the mass of this structure and the acceleration at the base of the structure, we can get V. V is the base shear under this structure. And this is gonna be the weight of the building, which is something related to the mass, like the mass of the building multiplied by the acceleration of the building. Let's not put the weight now, okay? So we need to find out the mass of the building and the acceleration of the building, okay? So that's actually the main objective, is to find what is the acceleration of this building, or an entire community getting hit with an earthquake, and this earthquake is gonna impact every building. Every building is gonna have different acceleration, okay? So we need to find out what is this acceleration. So engineers come up with this method, it's called the response spectrum method. This method, the engineers want to find a function on the x-axis, something related to the building parameter, like let's say building coefficient, like a parameter that can represent the building. Once you have this curve, you go here, you find the acceleration of the building. We need to find this curve. Let's say how engineers come up with this curve. All right. So before I do this, I want to talk about this system. What is this system? This system represents this building, right? It has all the needed parameters about the building that can impact the building performance. What are these parameters? The mass of the building, the stiffness of the building, the damping of the building. That's the important parameters that can differentiate building from another building. Like if we have this building and we have another building, these three is the three parameters that can affect this. Like let's say an earthquake is gonna hit a specific building, okay? So this building is very, very stiff. What is gonna happen? Like an earthquake hit, it's not like, this building is gonna make like this, right? What if it's flexible? It's gonna make more deformation. So we need to come up with something, a parameter that can combine these three parameters, okay? What is this parameter? It's called the frequency of the building, or the natural period of the building. What is that? It is the time that the building needs to make one cycle. Like if it's like there's a vibration or something, this building is gonna go this and come back to the original position. How much time this building needs to do this? So we have something, it's called omega, which is the frequency of the building. Let's put it omega here. And this omega is function of the stiffness and the mass of the building. This is if it's undamped system. Can you see we only have K and M? If it's damped system, C is gonna show up here, but let's focus on this undamped system, okay? If you guys are interested more, I have, I believe, 15 pages that have a complete seismic course. I'm gonna upload them on the on Canvas. You can look at the different systems, damped, undamped, multi-degree freedom, single degree freedom, but I'm just giving a summary that helps me to go to the response spectrum analysis method. Okay, so we are going with undamped, and that's the frequency, okay? So the if you guys remember, the natural period, or the period is always something. It's a 2 pi over omega. That's something simple. Like let's say frequency is actually omega is like what you call it's the angular velocity of the building. Like the angular velocity, like how much do you take to cut one cycle? Okay? So to find the time, it's like this is a velocity. Velocity is equal to the distance over time, right? Okay? So if you want to find the time, you divide the distance over the velocity, right? So the velocity right now, or we are not looking at linear velocity, we are looking at radial velocity, or a cyclic velocity. So we have omega, that's our velocity, and the distance that we cut is the 2 pi, which is the perimeter of the circle. So it's like 2 pi over omega. So that's where the t relation to the omega. So, and we have omega is equal to root k over m, so we're gonna have here root m over k. And that actually makes sense. Like if the building is very, very stiff, so I mean like the stiffness is very, very high, so the period is very, very small. Like the building is gonna make it's gonna come back to the original position faster, okay? But if the masses is big, means that the building are gonna go like this all the way and then come back. So it's gonna take much more time because there's a big mass here, okay? But if there is no mass here, this building barely moves, okay? All right, so these are the parameters that can describe the building. Like we can right now identify a building by its natural period, the time needed to make one cycle. Why? So we call the natural period is like the fingerprint of the building. Each building has its own fingerprint. Even if you have two buildings was built the same like each other, you are in a compound and the same model was built, it's still everyone has different construction control. Like some columns are like weaker than the columns here. The soil here is different from the soil here. Still there is some differences. So that's what we call the natural period, is something that identify a building from another building.
Professor, sorry, why is it that when wind or an earthquake hits that natural frequency, why is that causing the worst case scenario?
It's causing what?
The worst case scenario.
Well, the worst case scenario doesn't have anything to do with this. I mean, it depends on the earthquake, but definitely this is gonna affect the performance.
Correct.
Okay? So worst case scenario, like you have like, it's based on the hazard itself. Like you apply specific, you have a building by its own. You can't, once this building is built, you can't change this. This is constant. You're gonna hit with an earthquake, with an earthquake that has AG 1G, like one, the gravitational acceleration. If it's 2, it's more. If it's 3, it's more. So, but we don't design on worst case scenario. We design on the standards. It tells you to do this. This is a 100-year event, 1,000-year event. So you design based on the standards.
Yeah.
Okay, so right now we can, like, if we have a community that has multiple buildings, like let's say that we have a community like this and have building here, building here, building here, we can eliminate anything about the building. Once we know the masses and the stiffness, we can say that this building is T1, T2, T3, whatever. Okay? So right now, T, the natural period of the structure, is the identifier of the structure. Okay? All right, so we came to this point. So to develop a curve that can be generalized for many buildings, we are gonna put on the x-axis the T of the building. So once you identify the T of your building, you come in this curve, let's say T is 1 second. Okay? You come to this curve and then pick what is the acceleration. We call it the spectral acceleration. Okay? And then we go to this curve. But let's say, how do you develop this curve? So engineers did this. They said, how about if we come up with a spectrum of buildings? Buildings that have big T, low T, big stiffness, little stiffness. Okay? So they said here, we have a building like that has M1 and let's say K1, and definitely there's damping and everything. And building that has K2 and M2 until building that has MN and KM, right? And we are gonna subject all these buildings to the same earthquake. Okay, so you're gonna shake all these buildings. So you have here the time T, and here is the acceleration of the earthquake, and they are gonna be subjected to the same earthquake. All right. So every one of these buildings is gonna have a different response. All right. So this response is gonna be something like this. Let's say this building is gonna have, over time, and I'm gonna capture the acceleration of the building, U double dot. U double dot is the acceleration of the building. U double dot G is the acceleration of the earthquake. So this is gonna be something, let's say this building response is gonna be something like this. This building response is gonna be something like this. This building response is gonna be something like this. Every building is gonna have a different response. So after they did this, they said, okay, we are only interested in the maximum response of the earthquake. Like all these small deformations or all these small accelerations, I'm not interested in. I'm gonna pick the maximum, whatever it's positive or negative, because it doesn't matter if the building is moving this way or this way. So I'm gonna pick the maximum. So this is the U double dot 1, and this is the U double dot 2, and this is the U double dot N, okay? And then we are gonna have a curve, something like this, and here, and every one of these buildings, like if this one has M1 and K1, I can get T1, and I can get T2, and I can get T3 by substituting in this rule. And then I'm gonna plot all the points that has the U double dot. So I'm gonna have like this, points here, like this. And then we are gonna have something like this, right? Then we are gonna like find the median of all this. It's gonna be, for example, something like this, right? This is for only one earthquake, this earthquake. Then we are gonna do the same for multiple earthquakes. We need to cover historical earthquakes, artificial earthquakes, so that we can cover lots of bands of earthquake. So you are gonna have multiple curves, like another curve like this. So we're gonna apply the same thing. We're gonna take this earthquake out, put another one, apply it for the same building, getting different responses, plot this here, and then we are gonna have like a curve like this, another one like this, maybe another small one like this. And at the end, you are gonna take average and standard deviation for all these earthquakes. So you are gonna end up with a curve like this. That's what we call the response spectrum curve. What is the response spectrum curve? Is based on this analysis, the dynamic analysis of the single degree of freedom system. But you will tell me how I'm going to find, I have U double dot G. How can I find this? How can I solve for U double dot? That's what is the dynamic analysis course do. Like when you take a dynamic analysis course, you will be able to find out based on the information that you have and the earthquake information that you have, the building and the earthquake information. Once you solve it, you are gonna find this. Let me give you a little bit hint about how to do this. Maybe it will take 10 minutes, but maybe this, I believe, is a little bit important so that you understand what this happened. So this is a dynamic analysis problem. You have this model, something like this, all right? And you have the stiffness, you have the damping system, so you have K, you have mass, you have C, all right? And then this thing is subjected to any force. Let's say this is U double dot G, and this is T, and we have something like this. We need to solve this system. This is like a structure analysis problem. You have a beam, and this beam has a load. But right now, we have a building that has mass, stiffness C, and this is the load, is the earthquake load. To solve this, this is a dynamic problem. If you guys remember from dynamics, I mean engineering dynamics, like if you have a mass like this, let's say this is the mass of the structure, okay? And this mass of the structure is attached to a specific, like a spring like this has a stiffness K, and has a damping C, and this mass you want to push this mass with a force, for example, on the other hand, something like this, Ft. Right? So this system is the same like this system, right? This mass has a force T, want to move it, and what is resisting this is the mass, the stiffness, and C, right? So if this system doesn't have any force, this is gonna stay still. There's nothing gonna happen. But once you apply this force, this mass can either go in or out. Like it either can I go this way or this way, right? So that's actually if the mass is neutral. But we are gonna assume that this mass under this force is gonna move this way. So the movement is gonna be M U double dot, or let's say that the movement is that way, like here. Like let's say that the U or the displacement is that way. If you remember the second law, the Newton's second law, it's like it says that if you want to find the acceleration of a body under a set of forces, it is the summation of the forces in a specific direction is equal to the mass multiplied by the acceleration, right? So if you want to find the acceleration of the body, sum all the forces, and all the forces is going to be equal to the mass by the, if all the forces are balanced, like this is equal to this, so this is 0, so the acceleration is 0. To overcome this building, and I mean like to overcome the inertia of this building and move, this force needs to be bigger than these forces. So let's say how these two is developing forces. When you try to push this building, there's a force that's going to be generated in this spring, and there's a force that's going to be generated in this damper. So the force in the spring, as you know from the Hooke's law, B equal K multiplied by delta, by how much delta you have here. So the force here is KU, the displacement. C is something like K, it's a coefficient but multiplied by the velocity. Rather than multiply by the displacement, you multiply by the velocity. The damping is function in the velocity of the building. So these are all the forces on this system. If you want this mass to move, or the force of the earthquake is gonna make this mass to move, it needs to overcome the stiffness force and the damping force. You need to overcome KU and CU dot, okay? So let's put this system in this equation. All the forces on this system is, and let's assume that this is the positive direction. So I have Ft, I mean like the force function in time, it can be earthquake, it can be anything, minus, because these are in a different direction, minus K multiplied by U, minus C multiplied by U dot. All this is gonna be equal to the mass multiplied by the acceleration. All the forces is equal to the mass Ma. And actually we can remove A and put U dot, U double dot, okay? So we can say here that Mu double dot, and we can send these two in the other direction, plus C U dot plus KU is equal to Ft, okay? If this an earthquake force, so the earthquake force is gonna be something like, let's say Ft is gonna be the mass multiplied by the earthquake acceleration, okay? If it's shaking the ground with U double dot, so you multiply the mass of the building by the acceleration of the earthquake, so you can replace this by Mu double dot. So what is this equation, if you guys remember from math? This is a differential equation. Like you guys, a mass, if you have x squared plus 2x minus 3 equals 0, this is a second degree equation that you can solve easily. But since x is double dot and x is dot, this is not a regular equation. We call it differential equation. And if this differentiated 2 times, we call it second degree equation. And since it's function in U only, so this is homogeneous equation, okay? So solving this equation, you need to go back to the math principles. You actually, how to solve this, you assume U as a function of cosine theta and sine theta, and then substitute here and find the factor in front of cosine and sine theta. Once you solve this equation using math, you will find what is the U dot is equal to. And then we will be able to find this, okay? But you will tell me, is this gonna be an exact number? Because right now we have U double dot is a curve, but this is gonna give us an exact number. So if Ft is an exact number, like at a specific time, like only one spot, you will find U double dot at only this spot. But if you have it at T, you have to divide it at intervals, and you will be able to solve for the entire curve. Like you divide the analysis of the solution. So you are gonna get U double dot at each time interval, and then find this, and you apply the same thing for each system. You are gonna replace the mass, replace the C, replace the K, and then put the same earthquake force, and then get the solution for the second one, for the third one. This is how we solve for the seismic force analytically, okay? So there's a special thing about this equation. We call this part, as I told you, this is second degree differential equation, okay? Because we have U double dot. If it's only U dot, so it's gonna be first degree. This part, we call it the resisting function. This part, we call it the forcing function. And actually the way we solve this, if this is a single degree of freedom, it's gonna be a single equation. And that's why I'm telling you it's much easier. But if you are gonna make a multi-degree of freedom, this thing is gonna be a matrices. Like you are gonna have a mass matrix, and the mass M1, M2, M3 up to Mn, something like this. And all this is gonna multiply by the U double dot of story number 1, story number 2, up to story number n, plus a matrix for the C multiplied by U double dot, plus a matrix for the K multiplied by U, plus the FT is gonna be something here. So that's why I was telling you that this is a much harder to solve. Rather than having a one single equation, you are gonna have a bunch of matrices. Actually, if it's 2 by 2, maybe it's easier. I solved it some 2 by 2. 3, I did it as well, but it's much difficult. If it's 4, it's gonna be crazy to solve this equation. So you need like a programming tool or something so that you can solve much complex ones. All right? So right now we understand step by step how analytically this is done. You have a 3D building, you convert it to a multi-degree of freedom, then you got an equivalent system of a single degree of freedom so it can be easier to solve. We got the natural frequency of this building, the time, and then we use the responsive spectrum analysis by replicating this concept for multiple buildings, or we call it a spectrum of buildings. So you have building 1 up to building n. And apply the same earthquake to the same building, solve using the engineering dynamics here, and then you are gonna find the solution for each building. So you're gonna have U double dot for each one. Then we plot T with U double dot, and then we come up with the responsive spectrum. Does anybody have any questions so far? By the way, I tried to summarize a complete course of structural dynamics here, so not kidding. Yeah, so that's a complete course, but I give you some hints, like in the dynamics, you're gonna study this as a single degree of freedom. And then you are gonna do the same thing with damping and without damping. Multi-degree of freedom with damping and without damping. And you keep doing stuff like this. But this is the general concept. But the thing is, to do this, to study an earthquake on one structure is gonna be a very tedious problem. To do all this mathematical, we need to avoid mass. That's actually what the standard is doing for us, to avoid mass as much as we can. So the standards came up with some methods that you only account for some factors. And like, for example, like you go in the code and then first you find where is your building at. Like let's say Florida, you are gonna come up with an acceleration related to this zone. And then you are gonna use some design parameters. You will find a soil factor or a soil coefficient. And then you are gonna find like some factors related to the building. Like if it's a frame system, if it's something, so you're gonna use all the factors related to the code. So I'm gonna list here how the code is handled this, but this is how everything is handled analytically. But before I tell you about the codes, I need to touch base on something related to the mood shades of the building. Okay, so okay, so when I told you about the natural period of a structure, and actually it depends on the movement of the structure, right? Like let's say that your structure is like this. If your structure is like moving this way and this way and coming back to the original position, that's what we call the natural period or the versed mood shape of the structure, okay? And that's where this equation works. But the thing is, if the structure deflected or got a different shape while moving, it's gonna have completely different frequency, right? Like sometimes if the building is tall, the structure is gonna make something like this. That's not linear, right? That's something like this and make like this. And that's actually happen in tall buildings. You can see that mode. If the building is flexible, like not very stiff, so this mode contribution is gonna be very, very low, or the probability of this mode to happen is very, very low. But if the building is tall, actually it can make this, and actually can make something like this, like many nodes, something like that. So all these modes can happen in the building. So the thing is, when an earthquake hit a building, the building can have different mode shapes. Like let's say that the building is 4 stories, something like this, and got hit with something, with an earthquake. So the earthquake is gonna shake all these modes. It's gonna make all these modes contribute to the motion of the building. But the mode shapes of the building has nothing to do with an earthquake. That's something in the characteristic of the building. Like the building, if it's more stiff, that means like the modes are gonna be something different. Okay, so let's see how this look like. Like this building is gonna have like the first mode shape is gonna be, for example, something like this. These stories. Something here. Correct. So the first mode shape is gonna be something like this. Like this building is gonna make like this and go back to the original position. Or it can make something, for example, let's say like this, or like this, or like this. This is a different mood shapes of the building that the structure can make. And every mood shape has T. Like let's say this is T1, this is T2, this is T3, this is T4. All right? So we call this the natural period of the structure. Okay? Why? Because this is the very smooth shape and it has the biggest contribution. Like let's say if this building got shaped by a specific earthquake, what we do is we try to find, because I told you what we are interested at is the base shear at the building, like how much force at the base of the building was induced by the earthquake. And in general, force is mass multiplied by acceleration, right? So the acceleration right now is the acceleration of the building. Once we find it, multiply it by the mass. There's lots of coefficients here, but I'm giving you general. Like in this equation by the code, you will find this is divided by risk factor, multiplied by R. There's lots of factors, but in general, it's a mass and acceleration. And the mass, we use something is called the effective weight. What is the effective weight? Like in seismic, we don't use the entire mass inside the building, like, or the entire loads, because we said there's dead loads, there's live load. We don't do the same thing for gravity load. We multiply by 1.2 and multiply the live load by 1.6. We don't do this here. In earthquake, we assume that the building doesn't have a full mass. Definitely there's mass that can move, like the own weight of the structure is gonna be there, like there's not. But for live load, we multiply it by a factor. We multiply it by 0.25 or by 0.5 or by 1, depends on the nature of the structure. Like if we are very sure that the live load is not gonna go anywhere, we keep it. Like if you have a library and you have books or shelf, it's gonna be there. Nobody's gonna move it, right? But if there's people and there's an earthquake, everyone is gonna move. So we assume that the live load, the full live load is gonna exist. Like for residential building, W effective is like the dead load plus 0.5 live load. That's what the standards say, okay? So for the acceleration, it depends, like on the, as I said, on the T of the building. But right now you are telling me there is multiple T's. Which one I'm gonna pick? Like here, like if you remember when we got in this curve, we got only with one T. But if the building is not gonna be moving with one T 100%, that means every one of these T is gonna contribute, okay? So what we need to find is what is the contribution of each mode shape to the total movement of the structure. Let's say that this one has a contribution 8%, 80%. This one has a contribution 10%. This one has a contribution 7%. This one has a 3%. Well, so you will tell me, okay, so since we know that, we're gonna use T1, go in the curve, find A1, and then find A2, and find A3, and find A4 from the response spectrum curve. And then if we need to find the total beat shear of the building, you multiply 0.8 by MA1 plus 0.1 by A2 plus 0.07 by MA3 and so on. You're gonna do that. Well, it is not that way. I mean, like, we don't know, but that's actually, I mean, like, without going in very details, this is how it goes. So, you have a bunch of mode shapes that contribute to that total base shear on the building. Definitely there was like lots of matrices and lots of stuff here, but in general, it's kinda how each mode is contributing to the total base shear on the at the building. And we use this base shear, this base is something like this, to distribute the force all over the stories. Like the base shear is gonna shake the building, so all the stories are gonna take this as a forces. And the last story is gonna take the more forces, less until you go down. If you sum all these forces here, it's gonna be equal to the base shear. We apply these forces on the masses of the structure and see how much bending moment is gonna be generated on the shear walls, on the columns, and do seismic analysis. So this is the process, okay? So you understand the process from the analysis by converting to a single degree of freedom, and then find the responsive spectrum curve, T versus acceleration, and then we have a bunch of mode shapes. This mode shape, everyone has a natural period that has, a period, and then based on the period, it's gonna have a different acceleration, and each one has a contribution. And because actually, the thing is, if you have a tall building, 60-story, you are having, and by the way, the period, the natural period is not only in X direction. Like if this building is a regular shape, there is actually a movement can happen this way. There's a movement that can happen in the other way, in the Y direction, like it's gonna make something like this. But let's say a building like this, what is the versed mode shape of this building? Actually, that is the versed mode shape, we call it the easiest movement that the building can do. Easiest movement. What is the easiest movement for this building? Is like to make like this, or to move the other way. To make like this, that's the natural period. Okay, so that's the easiest mode shape that the building is gonna do. If it's much harder mode shape, it's gonna take more time. So definitely this is the least time. Like let's say T1 is 1 second. This is gonna be 2 seconds, or 3 seconds, or 4 seconds. It's gonna take more time to do. Like to make a movement in the other direction is gonna take like more time. And actually there is a torsional mode shape. Like the building can be rotated like this. And this happens when buildings has irregular shear walls. Like let's say for an example, you have building like this, and let's say you put a shear wall here, okay? Just this shear wall, and this building is gonna be hit with an earthquake this way. Do you know what is this building gonna happen? So that means like you have your building like this, and you hold it very tough from here. Like you make an element that is very, very strong. This building is gonna shake like this, around this tough element. So that's irregular. So the very smooth shape of this building is gonna be torsion. Because that's the force, the earthquake force is gonna hit in the CG of the building, and then once it hit in the CG of the building like this, it's gonna make this building to rotate. But if you balance this with a shear wall here, this building is gonna make an X movement. In design or the best practices when we design buildings, we need to avoid the torsional node, because we don't want our columns and shear walls to have torsion. That means extra shear reinforcement. So we need to have shear force. Torsion is gonna add moment and also shear on our columns, okay? So the distribution of the shear walls are very, very important. If you are able to make them symmetric as much as you can, that's, I believe, the best way to do it. So that's also contribute to the analysis. And also one note to take is we lump the masses. Do you guys remember when I was doing finite element analysis, I told you we make 2D model and we divide the mesh very small so that we can capture the bending moment at the different location of the slab. But when we do lateral analysis, we are not interested in the mesh, what is gonna happen inside. Whatever mesh size that you have, all what I'm interested in if the mass of the slab is right or wrong. Because inside the slab, if it's meshing, I don't care. All what I'm caring about if the mass is right or wrong, and if it's connected to the columns right or not. If it's not connected right, that means the stiffness of the column is not contributing to the movement of the mass, okay? So that's why we don't care about the mesh size when it comes to lateral load analysis. We can make the mesh much bigger, okay? So that's why we divide the mesh maybe 2 by 2, 1 by 1, because I'm not interested in the bending moment. So that's why I told you we'll make a 2D model separate from the 3D model. The 2D model is for the gravity analysis, and the 3D model or for the seismic analysis, and we make the size of the mesh much bigger. And then we make it as a diaphragm. What is diaphragm? We're gonna see all that in ETAPS next time. Like if your slab is like this is slab, the thing is, all our assumption is based on that all the columns in the same story are moving with the same delta, right? If the slab is not stiff enough to make all the columns move with the same delta, so this assumption is not right. But the slab is a very strong system. It cannot deform. It can deform if it's a very thin slab. Like if the slab, maybe if it's steel and it's a very small thickness, it can make like this. Like the slab actually, when the building has an earthquake, it can make like this. But if it's a very stiff slab, it's gonna make like this. So it's gonna take all the column this way or all the column this way. So if you didn't assign a diaphragm, or if you didn't define the slab as a diaphragm in ETAPS, your model is gonna take forever to solve. What I'm saying is by diaphragm is, we are telling SAP 2000, consider all the points on the slab having the same degree of freedom. So rather than having, like, let's say we have a mesh 1 by 1, and we have, let's say, 200 points on the slab, 200 joints, if you divide them. So if you perform the lateral load analysis on ETAPS 2000, it's gonna deal with every point as a different degree of freedom, and it's gonna solve to find what is the deformation at each point. But once you tell ETAPS that all these points are on a stiff diaphragm, we call it a rigid diaphragm. So that means I'm telling SAP 2000, don't solve for each degrees of freedom. All of them has the same degrees of freedom. So we reduce the degrees of freedom of 200 points. Each one has 6 degrees, different degrees of freedom, to 1 degrees of freedom. Like all the points are moving X or are moving Y or rotating about each direction. So that's also one of the points. All right, so I think I pretty much covered this part. Let's see how standards deal with that. Actually, I have a PowerPoint presentation rather than going through the writing on the board. So. Okay, so in this presentation, I'm gonna show you how the standards is handling. We are, in the standards, we're not doing all this mathematical work. Standards handling in a different way because this is a very long and tedious process. So let's say that you modeled your building, you select the lateral road resisting system on the structure, determine the preliminary dimension, which I gave you for the project, and then the next thing is that we need to have a 3D model, like the way that you have it, to apply the earthquake loads. All right? So, what I'm gonna show to you right now, how we perform earthquake equivalent lateral force analysis using the ASCE 716. So the first step is to identify where is your location. Is it LA? Is it Wisconsin? Is it Mississippi? Is it Florida? Florida is one of the states that has the lowest earthquake activity. Okay, so we are gonna assume our building, I believe, in Los Angeles, okay? So we are gonna go to the map. This map, I believe it's in figure 22.2 here in the standards. So like if you have the standards or a PDF of the standard, or actually you can use this. I'm gonna show you a software that's gonna do all this for us. But this is, to be honest, as an engineer, you should have, as a structural engineer, you should have the ASCE 7 that has all the minimum load designs for buildings. Like I would go to the map. Like we have here seismic maps here. Okay, so it's gonna be something like this. And then I'm gonna find out where I am. And then you are gonna find something is called the short and the S1 and SS for the zone that you are in. What is this? This is the earthquake acceleration in this zone. And we get two of them, SS and S1, okay? I'm gonna tell you why we do this. And then we need to have a soil report for your structure. We are gonna assume that the soil that we have is D, type D. There's different type of soils, A, hard rock, B, rock. We are gonna assume that it's D. But in real construction project, we are gonna have a soil report that is gonna tell us what type of soil that we are dealing with. Okay, so once we identify the soil type, we're gonna find something called site coefficient. The site coefficients, we are gonna get two coefficients. One is called short period site coefficient and one is long period site coefficient. Why we get short and long? If you remember, we have the response spectrum curve. It is like a period from 0 up to whatever number is. There's a part what we call buildings that has short periods and building that has long periods. Everyone is calculated differently. That's why we get two coefficients. So based on the soil class that you have and the SS that you got from the code, you will come to table 11 and then you will find out what is the FA here, over there, and what is the FV, what is the short period site coefficient and the long period site coefficient. We find the two coefficient, we're gonna do step number 4, risk targeted for maximum considered earthquake. So you take these two and then you multiply FA by SS and FV by S1. It's kind of like we need to amplify the acceleration of the earthquake based on the soil. So if you are on a stiff soil, that means your building have less coefficient. If you are on a loose soil, so it's gonna be more coefficient. It's like factoring how the soil is gonna impact the building performance. Then we find a new acceleration for this zone. Do you remember when I told you an earthquake is hitting a specific area? So we need to find the acceleration. But to find this acceleration, we need to factor in multiple coefficients, the site coefficient, the soil coefficient, and then we take these two and convert them to something is called design spectral acceleration. We multiply the values that we find here by 2/3 to get another set of values, okay? That's a standard procedure, okay? But all this is based on research, which is based on the analysis that we are doing here, okay? All right, and then we need to draw this response spectrum curve. That is the response spectrum curve, okay? So as you can see, it's only one curve, but all the parameters that we are calculating is doing what we were doing, getting buoyance and then making averaging. We need to find one single curve. This one single curve is divided into 4 curves. This one, and this part, and this part, and this part. Depends on how the building is performing. If it has a long period or a short period. So think with me, long periods that mean your building is maybe very, very flexible. Either it's a tall and make like long motion. So tall buildings, like buildings that we are dealing with in our project, it's like 5 second period, okay? But if you have a 10-story, it's gonna be maybe 1 second. If you have 2-story building, 0.1 second to make this motion. Almost very, very small period. So long periods has different calculations. So the codes gives you the equations to calculate each one of these curves. Like tell you from 0 to t, from 0 to tz to to, you are gonna use this equation. It's function in SDS, which we got it from here. And you multiply this by a bunch of numbers. And for part number 2, it's gonna be equal to the S design, it's constant. And then part number 3 is gonna be SD long over the period of the structure. And this is gonna be a different one. So the code gives us all the equation, but it will tell me why I need to draw the curve. If I know the period of my building, I can try to figure out where is it here and go here and substitute in this equation right away and get the spectral acceleration. So that's what the softwares do. But I'm telling you the process of how to build the response spectrum. Specifically, if you are doing a multi-modal analysis, you have different T's for the building. So maybe one of the T's are here and one of the T are here. So you need to find the spectral acceleration corresponding to each mode, okay? And here's defining what is each parameter that you have here. Then the next step is what we call the risk category. So let's say we have a residential building and we have a hospital. Which one is much higher that we need to protect more? Hospital, right? So it's have much higher risk category. So multiply the base shear force by a risk factor that is big, maybe 1.2 or 1.5, okay? So if we have a shelter, like if an earthquake happened, there's places are designed for much bigger forces, we call them as a shelter, like a stadium or a church or something. So we multiply the forces by a risk factor. Residential buildings are multiplied by 1. It's not a high risk category, okay? So like if you have a special structure you don't know if it's 1 or 1.5 or 1.25, you go read each risk category and try to figure out what is your building fit in each one. Like for example, let's say here, buildings and other structures not included, blah, blah, blah. And here, look at this. Facilities that manufacture, process, handle, store, use, or dispose substances as hazardous fuel or hazardous chemicals. So that needs to be much higher risk category, because if it's like failed or damaged, it's gonna affect the environment, right? So I believe hospitals and the one that we have somewhere here, but we try to figure out where is it, okay? So that's one of the things that we need to find out, and I'm gonna tell you where we are gonna use it. Okay, so the next thing, actually that's an interesting point. There's something called seismic design coefficients and factors. I don't know if I have time or not, but okay. So when we design for seismic is a really huge force. Like if it hit a building, this building is like it's a huge force. But there was 2 concepts to design for seismic. Either to make the building very, very stiff, like very, very strong. If it's gonna hit by an earthquake, it's not gonna move. But if it got damaged and failed, we have a big cross sections, okay? It's gonna be a disastrous, okay? Or we are gonna make our building flexible. Like, okay, if an earthquake hit, I'm gonna allow some damage, but it's not gonna lead to failure. Maybe we are gonna have some cracks. So it's either you make your building elastic, like if the building is moving, it's gonna come back to its original position without any cracks. We call elastic design. But this design is very expensive and the damage is gonna be very bad. Or we make it as an inelastic design. Like the building is gonna move and we are gonna allow the building to have elasticity. Like we are gonna have some cracks and it's gonna open and it's gonna return to its original position, but it's not gonna fail. And after the earthquake, we are gonna repair it. So it's gonna allow us to design the building under low seismic force, okay? And this is less expensive design. So what we are gonna have is gonna be something like this, right? So let's say we are gonna capture the delta of the building with the force on the building. The elastic design, if an earthquake hit a building with elastic design, we need to have a linear relationship. Like as the force increase, delta is gonna increase, it's gonna be something like this. Let's make the line. We're gonna have, for example, something like this, okay? So once an earthquake hit a specific force and the earthquake is gone, this building is gonna return to its original position. There is no inelastic deformation, okay? So F elastic is something like this, right? And the maximum delta that the building is gonna reach is gonna be something like this, all right? So there's elastic energy, like the energy are, like the earthquake energy pushed the building, it dissipated into deformation, and then the building restored the deformation back once the earthquake is gone. But there's another way that we can design the building in much lower force here. But the thing is, this building, the maximum elastic force that it can take based on the stiffness and the masses of the element is up to here. And once the force exceeds this limit, you are gonna have inelastic deformation. Like building cannot offer more forces than this. And it's gonna keep deforming. Like cannot take many forces. Both systems have the same energy. But this one, some of them is elastic and some of it is inelastic energy. This one have all of it as elastic energy. So we call this F inelastic. You know, it's something like, back in the days when they were designing cars, the cars was like a box of metal. Like it's really a huge box of metal. Metals are everywhere. Right now, cars, it's more plastic. Like if like back in the days, two cars hit each other, you will not find a car is compressing this way. Like it's like a very strong cars. But right now, it's more elastic. So how is the two different design concepts? So rather than having the driver absorb all the energy of the impact, you make the car deform and absorb all the impact into deformation. That's the same thing here. You make the deformation into this. And this allows us to reduce the seismic load. Can you imagine? Sometimes R equal to 5 times. Like let's say without R, you are gonna have 1,000-ton base shear in the building. But if you allow the inelastic forces, you are gonna make this base shear to 200. That, can you imagine how much the cross section is gonna be decreased 5 times? Okay, it's not linear, but I'm telling you, it's like 5 times reduction. So we call R is the ratio between the F elastic and the F inelastic. Okay, so that's the concept of reduction factor. Okay, so yeah, I mean, I'm not gonna go much in details because I don't have time, but this is a little bit of introduction about the response modification factor, which is R. And one other thing, I told you that the T depends on the mass and the stiffness of the structure. The standards has another equation that calculates T, which is a simplified one, but it's not the exact one. If you want to find the exact one, you need an app, like a software, analysis software, calculate all the masses, all the stiffness, and find the actual T. But this one is an approximate one as a function of the height of the building and the system, the structural system that you have. If you have a frame, if you have shear wall, if you have a steel, concrete, each one is different. It's a CT multiplied by HN multiplied by X. So let's look. There's a table that tells you if your building is a moment resisting frame, or your building is a steel moment frame, or a concrete moment resisting frame, or there's a shear wall. I believe here is the all other structure system, which is a shear wall. So you're gonna pick this number. This is the CT and this is the X. You go back, substitute in your equation, and you are gonna find the natural period of the structure. So standards provide you with some simplified equation that doesn't, like before you run the analysis for your software, substitute in this equation, find what is the value of T. Then build a model and see what is the actual value of T. Okay, so we have this, and then we substitute, and then we are gonna find what is the T for the structure. Okay, so one other thing that we are gonna do as well, since we are gonna design that our building is cracked, like we are gonna allow our structure to have inelastic deformation. What does it mean by inelastic deformation? That all the sections are gonna crack. Like if the building is having inelastic deformation, that means it's not gonna return to the same position, and sections are gonna open and gonna be cracked. So you need to model your cross sections as a cracked sections, not as a full cross section. How we can do this? The codes provide some stiffness reduction based on seismic design. If you are gonna do seismic design with inelastic deformation, so you need to model all the cross sections in the buildings as a cracked section or as reduced stiffness section. So doing seismic analysis, we reduce the stiffness of the column by 30%, so we assume that the columns are working at 70% efficiency. Walls, it depends on actually, in walls there's something called cracked and uncracked. Is like excessive cracking if we allow an elastic hinge at the end of the wall, but let's say we're gonna go with uncracked, like the columns 0.7. Beams is 0.35, slabs is 0.25. So when we do seismic analysis, we are gonna reduce all these stiffnesses, okay? All right. And here it tells you how to calculate the forces. I told you that we are gonna calculate the forces, the base shear here, V at the base of the building. But we need to find out what is the contribution of each story from this base shear. Like when you shake the building from the foundation, like this, all the masses are gonna move, right? We need to find what is each story is absorbing, what is the value of the force or the contribution from the base shear that each story is absorbing. And this depends on the height of the story and the mass of the story. If a story that has a big mass is gonna absorb more force. And if it's at a higher elevation, it's gonna absorb more force. Okay, so the code gives you actually the equation that can calculate the total base shear. So here you have something called CES. Yeah. So what we want to find out is V, right? VE is CS multiplied by the weight. I told you like V is a force. It should be multiplied mass and acceleration. Well, mass is inside the weight here, right? Because the weight, the mass is the weight over G, right? So definitely G can be inside this factor. And the acceleration is gonna be inside this CS. So basically CS is an acceleration. It's called the seismic response coefficient determined in accordance to this section. And it has acceleration inside it. Let's see how's the acceleration inside. It has SDS, which is the spectrum design acceleration that you get it from the responsive spectrum, divided by R. R is the reduction factor, so the acceleration is divided by R. That means that we divide the whole force by R. Multiplied, like IE should be on the top, by the risk coefficient. Okay? So when you divide by the IE can be, that makes this, like if this value is bigger, if the risk coefficient is bigger, like 1.5, so the 1.5 is gonna go up and make the forces much more. So you divide by R to reduce the forces, and then you multiply by the risk factor to increase them back, depends on the risk coefficient. And here it gives you different ways to calculate them, based on the natural period. If the natural period is less than TL, if it's more than TL. So I know standards has a lot of equations, but this is how buildings are designed. Yeah, this is analytical solutions, and there is a standard solution. If you design the building, you are not gonna go this way. You are gonna go with the standards way. And there's softwares that can do this for you, but it's better to understand analytically how this came from, and you better to understand how the standards are dealing with them. Not because I'm gonna show you next time in ETABS how all of this can be done in 2 minutes. Define the soil, define everything, and the software is gonna do everything for you. You're not gonna do anything. But I need you to understand what is behind it's going in software, because if something goes wrong, you need to find out what is each factor is affecting what, okay? All right, so I believe once you find the base shear, the next step is to distribute V over the stories. So basically we find something like the Fx is the story force and V is the total base shear. And this factor is the contribution of each story. Like Fx has a contribution of Vx, like let's say it's gonna take 0.1%. How to find this value? You multiply the weight of the story by the height of the story to the power 1 or 1.1, depends on the system, and divide it by the weight of each story multiplied by the height of each story. It's like a weighted average, okay? The weighted average of the height and the weight, okay? So this is how we do this. We're not gonna get in details how we find the equivalent forces, but if you are having a seismic course, you have to do all this manually, like you know how to do them. In our course, we're gonna do this by ETABS. So I believe that's it for now, and I believe you tried to chew on this information, understand what we are doing, and next time I'm gonna show you how to apply the forces on ETABS so that we can start the project. I believe last time is the last lecture for the project. Maybe we have one more lecture if we were not able to cover everything, but just 1 or 2 lectures, then we will get back to structure and the rest, okay? All right, see you guys next time.